Sorry, I told you, yes, I'll start at 2 minutes after 10, but I was muted when I did that. Now I'm going to mute. Ladies and gentlemen, it is 10:02. Time to start. My name's Roger. I want to first offer a disclaimer. I am not Greta. Greta is 60 years younger than I am and a lot smarter. But with that, I think we have a few things that we maybe owe her and her followers, and that's where we're headed today. We want to look at climate change, define the problem to some extent, but we mainly want to focus on solutions today. Some of you were here a couple of weeks ago, and I want to say welcome back. I'm sorry about the internet problems we had. And hopefully those are all fixed and we are now good to go. Okay, so let's take a look at where we're headed today. This could be a fire any number of different places, at California, Amazon, but in any case, the backgrounds of the slides today are going to kind of remind us of what we're dealing with. So we want to talk about what's going on, how serious. There's a lot of fiction out there. I want to at least just note what the fiction is, and then we'll progress through debunking the fiction. We're not going to spend a lot of time on it because what I'm looking for here is everybody to understand we've got some very cost-effective solutions facing us and some very serious work for the design industry to help get us out of this hole we're digging for ourselves. What will it cost? Pretty important. We're going to spend time on that, a lot of time on what it's going to cost. And of course, then there's a return on investment that's also important. We'll look at greener buildings, greener transportation, greener government, and greener ethics. Okay, this could very well have been a picture down in Central America just a few days ago. Imagine this is, I have lived in Florida for the last 51 years. I pay a lot of attention to when hurricanes are coming. I have never heard of a Category 4 hurricane hitting Central America in the middle of November before the season's supposed to be over at the end of October. So interesting stuff going on out there. And it's, I don't know, well, it's interesting, but there's a lot more than just interesting. Let's look at some of the fiction that we hear, because I'm sure you hear it as much as I do. Every once in a while we hear that climate change is a hoax. I doubt anybody in this picture would argue the point that it's a hoax. I think they feel that it's very real. I hear a lot that climate change is not caused by human, it's just part of natural cycles. And it's just a changing climate is temporary. Well, sorry folks, carbon dioxide stays in the atmosphere for several hundred years. And so even if we quit putting it in the atmosphere now, what's there would take almost 200 years to go back to the 1990 levels. So this is not a simple matter of all of a sudden quit using fossil fuels. Then there's a story about how, well, back in the 1800s, there was a dust storm or there was a drought for 10 years. Again, temporary stuff. We are not talking about a temporary thing here. This is a long-term thing that has been actually brewing for a couple hundred years, very slowly. Good examples are glaciers. There is a glacier up on the in midwestern Alberta that has been receding now for a couple hundred years probably, but in my lifetime that thing has receded by about a mile, and it's incredible. I couldn't believe where it was the last time I was there 2 years ago compared to when I was there 50 years ago. Unbelievable. There are people who say, well, it's so cold. Look at Minnesota got snow way before Halloween this year. So how could it possibly be global warming? Well, take a look at the temperatures in the southern hemisphere and ask me whether there's global warming. Okay, and again, we're not going to dwell on these things, but these are just things that I'm sure you've all heard. The average temperature hasn't changed. Well, guess what? If you look at the temperature between, say, 2000 and 2020, it's going steadily up, the average annual temperature of the planet. But if you draw a line that shows the average, well, sure, the average is the same for all those years. If you because that's what an average is. But every year, as you add another year, the average temperature goes up. But so, sorry, that is not an accurate statement. And all we have to worry about is sea level rise. I hear that a lot because I live here on the beach in Highland Beach, Florida, and everybody worries only about sea level rise, but there's a whole lot more to this thing than just sea level rise. But let's first talk about the difference between weather and climate. Uh, what you see here are pretty good examples of weather. Nice pretty day up in Minnesota there with that apple tree blooming. Nice cool day up in New York with a pretty an interesting snowstorm. Kind of chilly in summer in Newfoundland, that particular picture in the upper right, and one of the first cold days up in that same house that you see behind the apple tree. So what's the difference? I think we all know, but let's just make sure we've got it. Weather is the state of the atmosphere right now at a definite time in a definite place. In terms of heat or cold, wet or dry, calm or windy, clear or cloudy, and so forth. It's just an instantaneous meteorological condition, whereas climate is the average course or condition of the weather at a particular place over a period of many years. Uh, I noticed this in particular here where I am. I moved here to Florida 51 years ago, and typically the first really cold part of the year would happen, it would drop below 40 the week before Thanksgiving. We're just about there, and gosh, it dropped down to about 70 last night. So a little climate change going on here in Florida, as it's going in other places. One thing we need to keep in mind is that some places are actually getting a little bit cooler, or drier or wetter. So temperature is not the only thing we're talking about in climate change. There are other determining factors that are a part of weather. So let's take a look at greenhouse gases. I'm going to flip through this slide relatively quickly and remind you that all of these slides will be available to participants as soon as the program is over. And our host will, at the end of the program, you'll take a look at the chat box and he'll give you all the instructions you need for getting copies of these slides. Where if you want to review them again, you'll see all the text that I consider it almost an affront that if I read infrared as a form of longer wavelength radiation, you've already read that already, so I don't need to read that to you. You're not infants out there. You are. Our audience are adult thinking people, so who also can read. So, but what I want to do is explain this in the next picture here, because it's all about the radiation spectra. It's heat gain and heat loss and heat balance is what warming is about. If we look at the radiation spectra of the sun, which has a surface temperature of about 5,800 Kelvin, and the Earth, which has a surface temperature average about 300 Kelvin, you can see that the peak radiation frequency for the Earth is roughly, the wavelength is about 20 times longer than the peak wavelength of the sun light incident upon the planet. And the peak wavelength, surprisingly enough, is the visible region of the spectrum. Gosh, I wonder how that worked out with our eyes and all that. We can't see the ultraviolet, we can't see the infrared. But as you can see, all of the energy radiated away, and most of you probably have had thermodynamics. Everybody gets to learn thermo, and you learn about the radiative heat transfer proportional to the fourth power of the absolute temperature, and a black body radiation curves, as you see here. And so it turns out that certain wavelengths are reflected more than other wavelengths. And at that 10 to the minus 5 meter wavelength at the peak of the Earth radiation away from the Earth, Carbon dioxide makes it a lot more difficult for that heat to get away than if there isn't carbon dioxide in the atmosphere. And of course, we need some, otherwise it would be too cold here. So carbon dioxide is like a blanket, but if we make that blanket too thick, then we get a little too hot and sweaty. So we got to regulate the thickness of that blanket to keep our operating temperature of the Earth at about the right temperature. Okay, so some numbers for you because I know everybody loves numbers. We all know the sun's about 93 million miles away, slightly elliptical orbit of the Earth, so sometimes it's a little further, sometimes a little closer. But the sunlight intensity at the top of the Earth's atmosphere, if you integrate the area under that curve, it's about 1,367 watts per square meter. Okay, and if we then look at the intensity of sunlight at the surface of the Earth, it drops to about 1,000 watts per square meter. So the atmosphere does block about 30% of the incident energy from the sun. And fact of the matter is, certain wavelengths are blocked more than other wavelengths, depending on moisture in the air, carbon dioxide in the air, whatever else might be in the air. Certain things tend to reflect or absorb certain wavelengths. So this is our issue that to maintain a balance, the amount of heat incident on the Earth has to be equal to the amount of heat radiated back away from the Earth. And if that's those two balance perfectly, then we have an average temperature that remains pretty constant. But if they don't balance, then it either gets colder or warmer. And so that's the issue. And as carbon dioxide gets into the atmosphere, it tends to get warmer. I see something over in the chat box. I want to take a peek over here and see what there's two things added. What have we got here? Yes, okay. Well, let's see. I guess Greg wondered if we were starting. We did soon. And answer to the slides at the end, yes, absolutely. I think I commented on that as well. You'll be getting a message in the chat box at the end of the program that instructs you how to get a PDF set of the slides. Okay, and I hope you'll order them and share them as you wish, because I consider that a compliment. If you even charge money for them, I don't care. So I mean, this is a message that I personally, I happened to have a great grandson added to my family 2 months ago, and I figured he'll be around if he takes care of himself in the year 2100, if there's a planet left for him. So that's why I don't spend my time sitting on the beach. I'm trying to make sure that he has a habitable planet when he gets here. Well, he's here now, and I want to keep it a good place for him. Right now, he's born in the middle of a pandemic. Let's don't make it worse for him. And of course, I guess I'm saying I'm depending on everybody here to join with me and do our part to help as we see the solutions. Anyway, here's the problem, and we need to fix it. Carbon dioxide and other greenhouse gases, which can be equated to carbon dioxide as being 10 times stronger, 100 times stronger, 1,000 times stronger, whatever, and add them all up and you get an equivalent greenhouse gas or equivalent carbon dioxide. Okay, so let's take a look. You know, the irony, if you look at this picture for just a second, some of these houses have solar panels on them. And right now, I don't think too many people are living in those houses and using that electricity. But solar is one of the solutions. And we're going to talk about it and why it's cost effective. Many of you have seen this Mauna Loa thing. Having been born in 1943, you can extrapolate down that it was probably down around 300 parts per million. It's now up close to 412 parts per million. So in my lifetime, we've looked at an increase of over 100 parts per million of atmospheric CO2. And that kind of explains why when I was marching in a high school band in the St. Paul Minnesota Winter Carnival Parade at 10 degrees below zero, it doesn't get that cold very often up there anymore. But anyway, where are we headed with this? This is the real question: is where are we going? And there's a lot of possibilities. And what we need to know from this course, this particular graph, the take home, is that the scientists who study the effects of global warming and the points of no return estimate that somewhere between 425 and 450 parts per million, we reach a tipping point where we can't stop it anymore. All right, and we're at 413, and you can see that if we keep going the way we're going, by about 2035, we probably eliminated my great-grandson's future. Even number two, which is a moderate approach, it's taking a chance because we're stopping at 440 in 2050, and 440 might be too high. Hopefully not, but we don't know for sure. 3 would be a much greener approach, wouldn't it? 4 would be what happens if we stop using all fossil fuels right now, and we probably aren't going to do that. So maybe 3 is the most reasonable scenario, and we're going to take a look at how we can actually achieve that scenario if we get serious about this business, okay? But let's look a little bit more about the tipping points of things that are of concern with global warming. And it's, it's not just the polar bear on the melting ice having to swim a lot further and maybe drowning and maybe going hungry because the polar bear can't get out to feed early enough. But usually climate change is associated with sea level rise. Almost nobody in my neighborhood talks about anything other than sea level rise. I'm guessing in California, maybe people talk mostly about fires. But, there's a lot of things that can happen depending on what we do. There can be large-scale catastrophes in climate and in weather. We've had some really serious hurricanes in the last few years. But also human and biological systems can be affected. And of course, the big concern of the scientific community and why they're defining our current situation as a climate emergency is the possibility of irreversible global warming and irreversible climate destabilization and or complete extinction of climate level. Our friend Greta talked about this sixth extinction, and yeah, we're kind of in that. And the question is, how far is it going to go? So let's look at these 11 tipping points, okay? Kind of quickly, we'll go through them. You'll be able to look at them again if you order the slides. Total atmospheric water vapor. The numbers are straightforward, 970 BTUs per pound to evaporate water. So if you condense it, it gives off 970 BTUs per pound. The more BTUs you got available, the more pounds of water are going to vaporize, the more clouds, the more sunblock, which reflects some solar energy back out of the atmosphere during daytime cloudy times. But during nighttime, it's like a blanket, and it keeps the heat in. So it's a double-edged sword, the atmospheric water. But when the humidity reaches 100%, the vapor condenses. Vapor is relatively short lifetime in the atmosphere. It's not particularly evenly distributed. Ask the people in western Colorado about that, or in southern Florida, and you'll discover you get different answers. And ultimately, though, water vapor increases exponentially as temperature increases linearly. So it's an item of concern. Total amount of melting ice. Well, we've heard a lot about that. First summer of no Arctic ice was last year or 2 years ago. When the ice melts, it's easier for the sun to get in, and also fresh water on the top needs to stay on the top. So melting, when I say, as the ice melts, the ice reflects sunlight away. But when it's gone, then the sunlight is absorbed by the ocean, and all that heat warms the ocean even more. When the water gets warmer, it expands. So the sea level goes up about 80% as a result of temperature, and 20% from temperature, and about 80% just because warmer water is less dense than colder water. And that's why the warm water is on top and the cold water is on the bottom. And there are thermoclines. And anyone who's a scuba diver understands thermoclines. Tipping point number 3 is the albedo effect. This is a very interesting effect. When the sea ice, and we just referred to that, sea ice reflects the sunlight back from the surface, but if there's no ice, it all is absorbed. That heats the water more, melts the ice more, and it keeps going on and on and on, exponentially. Tipping point 4, melting permafrost. Well, a lot of carbon, not a lot of methane in the permafrost. And when the permafrost melts, it releases the methane. Methane is somewhere between 20 and 100 times more powerful gas than carbon dioxide. And the 20 to 100 is not because they can't measure it, it's just because pure methane is about 100 times more potent as a greenhouse gas. But methane does break down in a matter of about 5 years to carbon dioxide and water, and then it has the carbon dioxide effect. So if you average it out, it's about 20 times more. If you increase the greenhouse gases above the melting permafrost, guess what's going to happen to the permafrost? It's certainly not going to freeze more firmly. It's going to melt more. On and on and on, and it's going to let off more methane until it's all gone. And this is considered to be a pretty serious threat by those who think about these things on a daily basis. This is not the coronavirus. This is plankton, and they're dying, and they're a major source of oxygen. They absorb carbon dioxide, they release oxygen, and they're dying. And it messes up the oxygen cycle and the food cycle. And we tend to be worrying a lot about carbon dioxide, but we kind of depend on that 19 to 20% of the atmosphere being oxygen for breathing, and we are actually messing with the amount of oxygen in the atmosphere as well. So another item of concern, especially since plankton produce 50 to 80% of the world's supply. Tipping point number 6, transfer of ocean surface trapped heat to lower levels. Sometimes this heat on the top can circulate down to the bottom and force water from the bottom to the top, kind of like an eddy current, except a vertical eddy current rather than a horizontal eddy current. And by the way, I'm going to stop in a little while, and if you're making note of any questions you might have, I want to get through this part of the program, and then if you want to talk about it a bit, we can slow down and talk about it a bit. And then, but I do want to get to the solutions as quickly as possible, because that's what's really important for us. But I think it's kind of helpful to understand the problem, because then it's a little more, gives a little better reason why we need to start working on fixing it. So the issue here is, if you got warmer water on the bottom, when you think that it's colder and then it rises, then the surface temperature rises faster, and that means that it evaporates more, and that can be a really serious issue as far as extending the hurricane season into a 12-month season. And that's not just hurricanes, we're talking typhoons and all tropical storms that also find their way north, a whole lot further. Long Island, we got family there, and they've got some pretty nasty storms up there, and some of you on the program here today may be from there, and you know all about that. So it's all part of what we're doing to and here's the fires, loss of forest. Not only are we losing valuable resources, dumping a lot of carbon dioxide into the air from the fire, as well as particulates, but these trees convert carbon dioxide to oxygen. So as we get rid of our forest, we get rid of our carbon dioxide sinks. And a lot of people are thinking about how to absorb that carbon dioxide, and whoever is doing that, and I hope they come up with a good solution, because it's going to take everything we can possibly do, including even artificial means of getting rid of carbon dioxide if necessary and other greenhouse gases to the extent possible. So let's don't ignore the other side of the equation. But the carbon dioxide has to be converted back to oxygen, because if it's not, it takes an awful long time to decompose in the atmosphere. The green plants are so much better at doing it. Plankton is so much better at converting CO2 to oxygen. Otherwise, it just sits up there as a CO2 gas. Ultimately, it converts to oxygen and other things, but it takes a while. So again, losing forests contributes to an exponential process. Then there's a release of carbon from soils. Well, yeah, because not everything gets filled with water. I mean, we've got a lot of water soaked into our soils around here right now, where I am. But there are places in the world where the additional heat evaporates water to the extent that the soil is absolutely parched, as you see here, and it makes it really difficult for soil to store carbon. It releases it instead, increases atmospheric CO2, increases heat, and round and round and round again. Number 9, changes in major ocean currents. Interesting possibilities here, because if we change, for example, the Gulf Stream, if it slows down, and there seems to be some evidence that it's slowing right now, there are some countries out there, like Norway, that kind of depend on the Gulf Stream carrying a little warm water up there. So if it doesn't do that, then that involves additional serious weather and climate change patterns. So and crop yield is important. Depends a lot on growing seasons and so forth. And people in the Midwest certainly are concerned about this. Number 10, potential for global pandemic. Oh, that could never happen. A global pandemic, who are we trying to kid? But you'll notice the melting permafrost here. There's a lot of other things in there other than just methane that have been frozen. We got people who want to freeze their bodies for posterity so that in 1,000 years they can come back and see what the world is like. But there's also pathogens frozen in there, and nobody really quite knows what they are, but we're certainly exposing them as we cause the permafrost to melt. So, well, what's going to happen? Are we going to have, when we finally get rid of COVID-19, are we going to have another one then we're going to have to deal with? And are they going to come back more and more frequently, just like hurricanes or other things? People are concerned about this, and this is not the normal word on the streets, even though we're currently facing a global pandemic, and nobody has ever claimed that it came from melting permafrost, and I'm not about to be one to make that claim. On the other hand, people smarter than I am have recognized the possibility that we ought to be sensitive to. And finally, the total weight of rising seas and the melting ice shifting. And here we're talking about a nice engineering term. It's called coefficient of linear expansion. And usually we put expansion joints in buildings because there may be a 50 to 100 degree difference in temperature, and a temperature difference of 100 degrees over a distance of 50 feet or so can cause some significant expanding or contracting of materials, and so expansion joints are put in. Well, think about the planet with distances of thousands of miles, and then look at a 1 degree temperature change, and look at an expansion coefficient, and think about how far the plates on the surface of the Earth have to expand or contract as the surface gets warmer or cooler. And it's not hard to imagine what might happen if things are, they're kind of set up so they can slide back and forth a certain amount that they've gotten used to, but if they get hotter and they have to slide a little further, there's some really nasty stuff that can happen. And these are things that can be seen from space. So This could also cause some really serious things like earthquakes, volcanoes, tsunamis. I think it's pretty clearly established a tsunami that was a part of the demise of the Fukushima nuclear plants was part of shifting tectonic plates and an earthquake, which then caused the ocean water to have this huge tsunami. Uh, I never heard about tsunamis when I was a kid, but we've certainly had a couple of them in the last 20 years. And a super volcano, you know, people think about, oh, wow, look at these places like up in Iceland and look at Yellowstone Park and all the thermal activity under there. And if that thing ever were to blow, forget about Old Faithful and some of the other geysers there, but if what's under there were to really be, if conditions were to cause that to turn into a super volcano, we would lose the northern part of the United States. And my Minnesota homeland would be covered with volcanic ash. So 11th thing. All right, now that everybody's got the now that everybody's scared, and I didn't really want you to be scared. I just wanted to be aware. Let's look at how we can fix it. Okay. Personally, I'm tired of talking about it. I want to start doing something about it. And here's some things we're going to do, but we need to understand what's causing it. So let's take a look. When we make electricity, 35.6% of the electricity is made by natural gas in the United States, 27.8% on coal. Renewables account for 17%, and that includes not just solar and wind, but it includes hydropower and a few others. And nuclear is at 19.6% in the United States, and this is back in 2018, okay? They've changed a bit. Renewables have taken a bigger part. Nuclear is a slightly lower part now. And so nuclear and renewables are almost equal. And on a worldwide basis, renewables have now passed nuclear in terms of their percentage contribution of total kilowatt hours to the worldwide mix of energy. But anyway, this is what we have in the United States. So let's take a look now at how much carbon dioxide these sources produce. Well, coal is 65% of all of the carbon pollution of the electrical generation sector comes from coal, even though it's a smaller fraction, but burning coal produces more CO2. C plus O2 equals CO2, you know? So 12 pounds of carbon give you, what do we got? 16, 32, 44 pounds of carbon dioxide. So lots of CO2 produced by burning coal. Another third of it is from natural gas and only 2% from other things. And that would be like diesel generators and things like that. But for the most part, coal and natural gas, that's it. That's where the CO2 comes from. Notice that nuclear and renewables are not on this picture. So who uses this energy? Well, 37% of the energy we use is from electricity. 28% is from transportation, 22% from industry, residential, commercial, 10%, and other uses are 3%. So this is where the energy goes that we use in the United States. We need to know this because we need to know what we need to focus on if we want to solve the problem. So let's look at by sector. If you lived in California, you might recognize this campground because these is where people had ended up living after their houses burned down in a California fire. Electricity is responsible for 28% of all, and that is the generation of electricity is responsible for production of 28% of all carbon dioxide, and the actual amount, 3.17 trillion pounds per year. That's a bunch. Transportation, 29%. And we're talking about burning liquid petroleum here. And 28 plus 29 is 57, so that's a pretty big bite if we can look at the electric generation and transportation sectors alone. We've got 58% of the 57% of the problem in our hands right there. Industry, 22%. Now, that's not the electricity that industry uses because that's included in the yellow part of the pie, and the transportation part of industry is included in the transportation part of the pie. So this is energy that industry uses that's different from the transportation electricity sectors. For example, burning coal or natural gas as process heat. And then residential commercial, another 12% there. And again, the electricity goes to all the rest of them. But in addition to the electricity in the residential commercial, we got another 12% that is say the natural gas used for heating or the propane used for heating. It's basically fossil fuel use because that's where the CO2 comes from, is from burning fossil fuels. All right, and 9% is attributed to agriculture, and that's not agricultural trends. It's food processing and farm machinery and off-the-road vehicles and so forth. All right, so now let's break down these sectors a little bit. Transportation. How much of that transportation part of the pie goes for personal vehicles? Well, 58% does. Strange, funny, I should ask. Large trucks, 23%. Ships, 2%. Airplanes, 9%. Railroad trains, 2%. And other things, again, off-road vehicles and so forth, another 6%. So, wow, if we can look at personal vehicles and large trucks and get rid of the CO2 production for them, that becomes pretty significant, doesn't it? So again, we're looking for what are the targets? Where should we be working on this thing? And we all can't necessarily work on all of them at the same time. On the other hand, we could all buy electric vehicles. I'll show you why that's a good idea in a little while. So, worldwide, what's out there anyway? What are the possibilities? Well, here is a graph in the 2016 version of my photovoltaics engineering textbook. It showed the graph up through 2014 and the contributions to total kilowatt hours, which are expressed here in quads, but quads are just large units of energy, 10 to the 15th quadrillion BTUs. You notice that crude oil is still at the top of the list here. Coal is right on up there with crude oil, and natural gas. So crude oil, coal, and natural gas are both all in the neighborhood of 100 to 150 quads per year, okay? And you can see where I added some data points recently to see what's happening with these curves, and I did a projection in 2014 of where these curves might be heading, and it's interesting that we're staying pretty much on track here. The blue one is hydropower. So here in this graph, we're separating hydropower from other renewables. The one that's hand in hand with the blue one since 1989 is nuclear, but notice that starting in about 2009, hydro started overtaking, and a lot more hydros out there now than nuclear. But the green one is the exciting one because that's renewables, and that, you notice that's a logarithmic scale on the left-hand side there, on the vertical side, which means that a straight line is an exponential increase, which is the sort of thing we're looking at as a bad thing as far as climate change. But in terms of the adoption of renewables, this has been happening exponentially for a long time, since almost when the first photocell was deployed. It's been growing exponentially, and if you look around you, there's still a lot of rooftops available that don't have solar, aren't there? So it's not that we have to quit installing solar, and it's not that we have to quit installing wind, because there's plenty of opportunity yet for including these. So again, we say, where are we going with these up on the top, these fossil fuels, these three petroleum, coal, and natural gas. We have to make some pretty critical decisions here. Are we going to keep going as we've been doing historically? And I think we know the answer to that. That is a red light. We can't do that anymore. There's an orange light that would say or the red light is the idea of increasing. The orange light is a warning sign that says, no, probably not a good idea to even stay the same. So the green path of decreasing the use of fossil fuels is really the only reliable way that we can for sure, well, not even for sure, but it's our best bet. It's our best option at ensuring a reasonable future for our children and grandchildren and great-grandchildren. So anyway, what do we got here? Let's try a scenario. This is my scenario, okay? Because anybody can do this. Take a guess. Start with where we are. Okay, the blue is all of the other use. Take it from one of those graphs. They're from the United States Energy Information Agency. Pretty reliable information. No fake news there. All right. And so just assume we don't make any changes in anything other than just transportation, electrical generation, and industry. This means no change in residential, no change in any of those other uses of electricity. And what does it show? It says that if we drop by 10% a year by 2029, the transportation, electric generation, and industry are no longer contributing to total United States carbon dioxide emissions. If we can do it, okay? Maybe we can't afford it, so we need to look at that. Maybe we don't have enough resources, maybe whatever, who knows? But we just saw a graph that shows that it's highly likely that we can get up into the range of energy production of fossil fuels with renewables in a 10-year time frame. So got to keep that in mind. That's really important. All right, so here's scenario number one. But, we don't have to stop with just one scenario. We can imagine something even slightly more aggressive. And this one says, let's slowly decrease the production by other. Same thing for transportation, electric generation, and industry. 10% a year starting, and notice those steps are the same size. We've got a linear scale on the left-hand side. So it means we are dropping by the same amount every year, 10% of the original value, where the blue ones are dropping 10% of the previous value. So that gets diminishingly smaller. But this is 5% annual reduction in the other sources that might even be able to do that. And that gets us down to, if we look at 5 gigatons of emissions in 2020, which is probably about where it's going to be. We don't know for sure yet, but it gets us below 1. So that means in 10 years, we can reduce our emissions by 80%. And that would be a good thing. Okay, and if we look at another scenario that uses maybe a little bit more wind power and do a 10% reduction in the other sources, including the same reduction that we originally proposed for transportation, electric generation, industry, then we get down to about a half of gigaton by 2029, which is a reduction of 90%. In 10 years, 90% in 10 years. Nobody's talking about doing this. So it must be too expensive or something. But if we did, what would it cost? Well, first we'd have to eliminate coal, which means we'd have to replace 1.15 trillion kilowatt hours with renewable generation. If we're just talking about electrical generation, turning it completely carbon-free. So we'd have to figure out what it would cost to replace 1.15 trillion kilowatt hours with renewables. We'd have to figure out what it would cost to replace 1.47 trillion kilowatt hours with renewables. And we have to figure out how much energy storage we need to have some of electricity available at night if we're making this with solar. And wind is a little bit unpredictable as well, so we kind of need to store a little energy there as well. So we need to take a look at the cost of energy storage as well. So let's look at coal first. How much is it going to cost to get to eliminate it? Well, 716 million kilowatts of renewables is what it will take to get rid of the coal 1.15 trillion kilowatt hours. Okay, that uses an estimate of an average of 1,500 kilowatt hours per year per kilowatt of renewables is where that number comes from. And if 80% of this is at utility scale, it's going to cost about 1.72 trillion US dollars at today's prices. If 20% is at residential scale, cost is about $0.43 trillion at today's prices. 1.72 trillion. Where have I heard that number before? Isn't that about what they're talking about for pandemic relief in 1 year? Oh, interesting. So total cost, 2.15 trillion for utility plus residential, which if we do it over a 10-year period, which is what we're proposing, we're looking at 215 billion United States dollars for 10 years. Now we have to realize there's a return on investment here. This is not something that we're just trying to stay afloat. This is something we can put money into and get money back as a result of it, because after all, we're selling this electricity. What about natural gas? What's that going to cost? Well, here this 918 million kilowatts of renewables will cost about 2.75 trillion US dollars, or 275 billion a year for 10 years. Can we do that? Well, we know that the gross national product is about 22.8 trillion, and guess what? We're already spending 700 billion a year on military. This is more than what we're proposing to spend here. And are we at war here, or what are we at? Because after all, this is pretty serious stuff we're dealing with. And for less than the United States annual military budget, which by the way is all spent by the United States government, whereas most of this money we're talking about here would be spent by you and I as investors, and much of it would be earned by you and I as people who implement these scenarios. So bottom line, it's affordable. We can do it if we set our minds to it. Okay, so gee, what about storing energy? How much does that cost? What you're seeing, by the way, is a little challenge that Elon Musk made to South Australia in 1917. Those windmills you see there, let's back up just a second here. Get rid of that. There's a lot of wind in South Australia and a lot of desert areas, you can notice. And they're having a little problem with grid stability because of wind existing and not existing. And so it appeared that a little energy storage would be nice to save excess wind power and then deliver it back. This is a 100 megawatt, 129 megawatt hour storage facility that Elon Musk proposed that he could build it in a month or in 100 days, and if he couldn't do that, he would donate it for free. You know, how can you pass up on a deal like that? Well, it was built in just over 90 days. Can you imagine even permitting something like that in 90 days in the United States? But anyway, these are lithium batteries, 100 megawatts worth. A lot. And that 100 megawatts can keep on cranking out 100 megawatts for about an hour and a half. Okay? But in that hour and a half, that's enough time to get some other power plants up and running. So it's a fine way of stabilizing a grid. Now, the batteries aren't the only thing out there. There's pump hydro, there's compressed air, there's double area capacitors. These things are all, the double area capacitors are not quite commercial yet, but flywheels are. And there's at least 10 different battery technology. And if we look at electric vehicles, we're going to look at those a little later because they're an incredible opportunity for energy storage. And instead of lifting water, you can also lift cement. If you can imagine a bunch of cranes that lift huge blocks of cement or steel and then let them fall back down to earth again, just like dynamic braking on a car, and generating electricity in the process. So when you have extra electricity, you lift the steel. When you need electricity, you let the steel drop, just like water. It just takes weight. Potential energy is mass times mgh, isn't it? So the higher, the more mass, and the more height, the more energy you got. All right. And when these things are commercial, it means they're cost effective. You don't commercialize something unless you can make money on the deal. Right now, storage, depending on what you're going to store, is priced at roughly $125 per kilowatt hour. And in storage, you don't just talk about kilowatt hours. You also have to talk about kilowatts, because you may have stored 10 kilowatt hours, but it may take you 10 hours to get it out. And if that's the case, then that's only one kilowatt of power that's available, but 10 kilowatt hours of energy that's available. So we need to pay attention to kilowatts and kilowatt hours when we talk about energy. Okay, so if a source is a megawatt and a megawatt hour, it will deliver a megawatt for an hour. This is something that's these are the two defining factors for example, for the Tesla Powerwall. Let's see what's happening. My thing dropped down. Maybe there's a comment. We're going to take comments in just a minute here. The cost of 4 hours of storage at 100 million, if we want 100 million kilowatts, that would be 400 million kilowatt hours of storage. And it might be from pumped hydro. That one on the lower left is one of those flywheels. We got a couple of different battery technologies, lithium and flow batteries up on the right-hand side. We're looking at 400 million kilowatt hours, and at $125 a kilowatt hour, that's $50 billion. But keep in mind, this capacity is available on a daily basis. It's not an annual amount. You can charge and discharge in one day here. So annually, that's a whole lot of kilowatt hours you can store and save and send back again. So you just store it when you've got extra energy, and you feed the grid when the extra power or extra energy is needed. And you let the power company decide when they want to buy some extra energy from you or some extra power. All right, so you have to have, obviously, short-term storage and longer-term storage. You need short-term to get through the peak hours, and longer-term to get through the night or through a cloudy day. So we need to be thinking about short and long-term, and whether it's going to be local, neighborhood, or regional. And interestingly enough, an electric vehicle, if we had 100 million of them out there, and level 2 charging is at roughly 5,000 watts. So if you charge a vehicle for an hour, that means you save 5 kilowatt hours in an hour. So what this means is, if your car is plugged in and you're at work during utility peak, there might be 500 million kilowatts and 500 million kilowatt hours available for no extra charge, because you already have the storage in the electric cars. So add that to the total cost of storage, and it doesn't add any additional cost other than, well, you decide whether you're paying for the cars or for the storage or some combination. Okay, so the other thing is that storage costs are declining because the technology, I mean, storage is a big ticket item now, and the cost is going down, just as the cost of solar is going down, cost of wind is going down. Technology is getting better all the time. So when we talk about doing these things at today's prices, the prices in 2030 are going to be a lot less than the actual cost. And if we take inflation into account, it gets even less expensive. And you've seen this happen. We've all seen it happen. A TV set that cost $2,000 is now $500. Whatever. Electronics is just getting so much less expensive all along that you almost don't want to buy a TV set because you want to wait for it to get cheaper. And then the thing is, every year they get cheaper, so therefore you may end up not watching TV, and that might be good anyway. So anyway, let's talk about zero energy units now. And you know what? I want to take a look here, folks, and see what do we got for time. I've been kind of rushing, but we're making reasonable progress. Come on, phone, tell me what time it is. Well, now this is interesting. My telephone doesn't want to tell me what time it is. So I could always do it the old way and look at my clock. Oh yeah, we're doing fine. Okay, let's look at a new concept. Oh, here's a Q&A. Okay, good. Let's see what we got here. And there, what about worldwide CO2 production? What percent is due to the U.S. versus other countries? You know, that's a good question. I'm not sure right now. I think the United States is about 20% of worldwide. What I can tell you is that China is way ahead of us in terms of adoption of renewables. I have another presentation where we deal with that, and I'm not real good at memorizing numbers, but this is a really good question. The Europeans are way ahead of us in terms of reducing their CO2 production. And the point is, we are followers right now. We are not leaders. And it would be nice if we could come back and become leaders. All right, so that's my answer there. And it's not hard to look this up. You can Google this afterwards and just say worldwide CO2 production. You get the answers from places like International Energy Agency. Why do I not see solar as part of a wind farm? Well, you know, it's interesting. Good question, Russell. That just happened to be a wind farm there, where because it's an area where there's a lot of wind, and wind is cost effective there, but they certainly could have had solar there. But then again, you can see a lot of solar farms out there where you don't see windmills either. So there's lots of solar being built. I can tell you that Florida Power and Light, their energy research arm, Next Era Energy, is building solar in Florida as though there's no tomorrow. Methane, natural gas, production of electricity, it takes about 9/10 of a pound of, for a kilowatt hour of electricity. It's about 9/10 of a pound if it's generated by methane. And Florida Power and Light is down to 0.86 pounds of methane per kilowatt hour generated. So that's kind of interesting. And it's a good question. But solar and wind are both out there. We just happen to see windmills are kind of pretty pictures, and I guess solar farms are as well. Actually, my basic expertise is in solar. Degree is in electrical engineering, but I've spent a lot of time on solar in the last 20 years. So let's see, I'm going to click these as having been answered. If you want to continue on those two questions, you feel free to add more if you feel that I haven't covered it adequately. I want to see if there's something new in the chat. Oh, thanks, Brooks, 10:57. Yeah, that's what my clock says too. I have a clock in my room here, but it's hard to see the hands on it. It's one of those it's a little dark in the room and I can't see the hands on the clock. Okay, so Let me close my Q&A and let's look at, some of you may have studied a little bit about zero energy buildings, but let's see what that involves. It doesn't mean you don't use energy, not at all. But it means that you define a site boundary and then you build something within that site that uses energy. And within that site, or sometimes outside that site, you build a renewable energy producer, whether it's wind, whether it's solar, whether it's both, whether it's something else. It's something that's produced within this site and delivers energy to this defined building, okay? And the next thing that happens is the renewable doesn't produce it as much as you need it all the time, so you have some delivered energy, which may have some renewable energy as a part of it, that you buy from the utility to round out the energy needs of this campus, okay? Or building, or however you want to define it. It could be a microgrid, for example. And there are times when this, whatever you have in the green box, is making more energy, that is within the site boundary. There are times when there's more energy being made than is being used. So that's exported. And zero energy simply means that the delivered energy equals the exported energy. So that's zero energy. And doesn't mean you're not using it. It just means that you're exporting as much as you're importing. And of course, the timing may be different. So there may be some need to save some of that exported energy for use at another time. But with this as a definition of a zero energy building, let's move on and see what happens next. First of all, in order to define zero energy, we have things called source energy conversion factors and imported electricity. That is electricity which is typically generated by some heat type process. And as everybody knows, thermal process, you got this 1 minus T2 over T1 kind of thermodynamic efficiency, which limits efficiencies to the 30% range. So that means it takes about 3.15 units of BTUs in coal to make electricity, or even natural gas, or whatever other renewable, or whatever the source is being used. So if you export renewable electricity, the source energy conversion factor, I mean, it's a matter of what fraction of the sun can you convert to electricity, but we have to be fair about it. Electricity is electricity. Electrons are electrons. So if the imported is 3.15, and if you can replace a kilowatt hour of imported with a kilowatt hour of renewable, then you're saving 3.15 units of source energy in the process, because then you don't need to generate that 3.15 units of imported electricity. Natural gas, 1.09. So a little more efficient there, because natural gas is probably going to be used for water heating, and that's roughly 90% efficient. Fuel oil, kerosene, diesel, well, multiple uses there, 1.19. So you can see these different source energy conversion factors depending on what the energy is coming in from outside, how much energy it takes to provide 1 unit that's imported into the zero energy campus. Okay, and so if you do that, this is the way we estimate whether we have a zero energy building or not. This one may be zero energy at this point because I can't imagine living there. But that's the wrong kind of zero energy, because that means they aren't using any because it's not connected. But anyway, we're trying to avoid this. So a little bit of math, because I know you all like math. You know that a kilowatt hour is about 3,413 BTUs. Some would say 3,412, but we're not going to fuss over that last digit. But that's 100% conversion, okay? A therm is 100,000 BTUs. Barrel of oil will give you about 5,800,000 BTUs, and a gallon of fuel oil number 1 will give you about 137,400 BTUs. So that gives us the water heating capability of these various sources. So let's make a list of what we're going to use in this proposed building and then convert them to source equivalents, okay? So when they rebuild this building, if they decide to rebuild it, they might want to consider building a zero energy building, okay? So let's assume that this building is going to use 7,500 kilowatt hours a year of electricity and 500 therms of purchased natural gas. And it's going to be your job to calculate exactly how much of this electricity and gas is going to be used by this super efficiently designed building that you've got on your drawing board. And so if we convert the electricity, we got 340, we have to first convert to BTUs, all right? So the direct conversion of electricity results in 25 million, 25.5 million BTUs per year, roughly, okay? And now we convert that electricity to source energy by multiplying it by the 3.15 factor, gets us up to 80 million BTUs. Then we look at the natural gas using the source factor 1.09, and that means the source energy used by this building is going to be 54,500 BTUs, 54,500,000, I mean. And so the total is 135 million BTUs of source energy per year. So now, all we have to do is make this many equivalent BTUs with a photovoltaic system or a windmill system or something. But since I like PV because I know how to do PV, naturally we stick with things that we're more familiar with. Let's see what size PV system would be required and whether it's even practical to generate this many BTUs. Okay, here we do the design example. Unshaded south-facing array in a lot of locations will generate roughly 1,500 kilowatt hours per kilowatt per year. And the National Renewable Energy Labs has a program called SAM, System Advisory Model, SAM, which you can download and you can put in your exact precise location and exactly the orientation of your photovoltaic array, and it will tell you to a good estimate how many, on a monthly basis, how many kilowatt hours you're going to generate in a year. Okay, so this is 1,000 watts of solar. You can expect about 1,500 kilowatt hours. If you're in the desert, expect about 2,200. Some places it'll drop to 11 or 1,200. Rarely drops below 1,000, even if it rains a lot wherever you are. Okay, converting this BTUs to kilowatt means we've got, or the kilowatt hours to BTUs means we're getting 5 million BTUs per year per kilowatt, okay, of solar installed. And now we convert this to source energy by 3.15 to make it equivalent to the other source energy things that are being used by this building. And it means we need 16,126,425.417, but I rounded it off a little bit, BTUs per year per kilowatt of, no, this is not, wait, BTUs, yeah, per kilowatt, okay. So that means a kilowatt gives us 16 million, okay. We need 135 million, so that means we need 8.38 kilowatts. Well, you know what? You can install that for about $3 a watt, so that's around 8,000, about $24,000 investment. If the array is 20% efficient, it'll make about 200 watts per square meter. All right, and so how many square meters are we going to need? We're going to need about 41.9 square meters, and that's 451 square feet of south-facing roof space. Hey, that's probably doable for a house of this size if you make sure you have some south-facing roof. And therein lies the challenge, because if your roof faces east or west, you're going to lose about 15% on the deal, and you're going to have 15% more solar to do it. All right. But still, 451 square feet, we are not at 4,510 or some unreasonable number. Says we can do it, all right? With 300 watt modules, it'd be an array of 28 modules. I mean, a 10 kW system in my neighborhood is pretty routine these days. Uh, Need to check the dimensions of the modules so they fit on the roof. But this is something you can show. And incidentally, by the way, the kilowatt hours, you would have to, if you sold that electricity, you'd have to get about 6 cents a kilowatt hour in order to pay back your cost of installation. And it's not that hard to sell that electricity for 6 cents a kilowatt hour. Let's look at heating and ventilation air conditioning systems. Here's a nice little heat pump that Mitsubishi has that has an SEER of 33.1, works down to about 13 degrees, minus 13 Fahrenheit. And 33.1, that seems unbelievable for seasonal energy efficiency ratio, but fact of the matter, as I was looking up some more heat pumps just yesterday, and there are inverter technology heat pumps now, the mini split systems that have SEERs as high as 40, which is like 4 times more efficient than the air conditioners we were installing even 15 years ago. So pretty substantial savings here. Again, you need to do the energy analysis, but these are commercial. So therefore, if they're commercial, it means they have to be cost effective or nobody would buy them. Then there's energy recovery ventilation. If you need to control humidity, it means you're going to have a very tightly sealed envelope and you're going to import outside air, but at the same time you bring the outside air, you're going to be sending inside air out through the other direction, and we're going to be exchanging heat between the two flow patterns, and therefore the outside air that's coming in is going to be cooled by the cooler inside air that's being eliminated, and we're looking at close to 90% efficiency here. You need a condensate drain if you're going to be squeezing water out of that inlet incoming air. But this is just for ventilation to make sure people stay more healthy in their building. So it's another feature of zero energy buildings is they are healthier. If you don't need humidity control, then you can just use a heat recovery ventilator and that will take care of that. Domestic water heating, what's new there? Well, you can look at electric water heaters versus solar water heating. You can look at, once upon a time, photovoltaic electricity was really expensive. I mean, 25, 30, 40 cents a kilowatt hour. But right now, like 6 cents a kilowatt hour. So 20 years ago, 40 years ago, solar domestic water heating was a whole lot better deal than heating it with water with electricity. Nobody would even think about it then. But now, if you use photovoltaic electricity at 6 cents a kilowatt hour, plus a heat pump water heater with a coefficient of performance of 3.5, then it only takes 1 kilowatt hour of electricity to make 3.5 kilowatt hours worth of water heating. And so it's very likely, if you do an economic analysis here, that the water heating heat pump will be your least expensive long-term choice. And if you haven't looked at one lately, here's a 50-gallon unit, and I saw something come up here. Let's see what the Q&A here is. Hold on. What's the cost per kilowatt hour per hour for each energy source? Well, okay. What I'm going to give you are cost per kilowatt per hour, which means basically cost per kilowatt hour. Mark, there's a process called, an economic analysis process called levelized cost of energy. You might be familiar with it. And this is one where I've memorized some numbers because they're so impressive. Nuclear, and what is levelized cost of energy? You're taking all of the costs associated with an energy source from construction to decommissioning and maintenance and fuel and the whole 9 yards. And then you figure out what's your break-even point. What would you have to charge for the electricity in order to pay back your investment? Nuclear, 9 cents. Okay. Wind and solar are down in the neighborhood of 6 cents Natural gas is a little more than 6 cents. Coal is more than 6 cents. And this is not including environmental costs. So the bottom line is renewables are not cheaper than fossil. Just that simple. Uh, Onshore wind is below 6 cents. Offshore wind is at about 6 cents. And you can look these up. They're not too hard to find. I have them in a different webinar. And again, I haven't got them completely memorized, but they're sufficiently impressive that it's a shame not to use them because it's the cheapest way to make electricity. And the proof is in the fact that the utilities are building them like there's no tomorrow. It's their cheapest way to make electricity now. And they're starting to get into the energy storage because they understand that they have to have energy at night. All right, so that's a good question. I appreciate it. Keep up the questions. We want to talk about them for sure. Thanks, Mark. Let's see, anything else up here? I keep looking. I don't want to leave anybody out here. There's something over here in the chat box. What do we got here? Do I know of an ERV? Okay, I don't remember the brand. I'm told that they can run at about 90%. You need to look at the specs on an individual. The ones you see are 55% transfer. I could be wrong. I could be wrong. I may have read something incorrectly. And let's see. Heat pump water heaters take heat out of the air to use. That's correct. Yeah. And the unit I show needs 700 cubic feet of space to be located in. Okay. And what's happening is you're taking heat out of the air and putting it into the water, which means, and in fact, it's interesting. I was talking to my accountant just last week, and he's got one of these in his garage. And he says it acts like an air conditioner in his garage because it's taking the heat out of the air in the garage, and therefore it's a whole lot more comfortable in his garage with the water heating heat pump there. So yeah, you got to follow the installation instructions when you install these things, but there's certainly 700 cubic feet in a garage. So, and if you don't have that, and again, 700 cubic feet depends on how much water you use, because if you use less water, you don't need a full 700 cubic feet, but I'm sure the specs say that. And this thing about ERVs at 55% could be. I can't argue the point on that. I appreciate you pointing that out. Let's see. Okay, I have to remember to look at the chat box more often. All right, let's see how a DC to AC inverter can be used for power factor correction. Okay, let's see, DC to AC inverter. Usually a DC to AC inverter. Okay, and we're talking like for solar, for example. These things are designed as current sources. Okay, and why is that important? Well, that's important because the utility is a voltage source. Basically, no matter what you plug into it, the voltage remains nearly constant. You can use about as much current as you want. Okay, of course, you're limited by the wire size and the circuit breaker size. So because the inverters are current sources, they use the utility voltage to synchronize. And UL 1741 or IEEE 1547 up until 2020 had required inverters to operate at 100% power factor, meaning that the current injected into the line had to be exactly in phase with the voltage. But now IEEE 1547/2000 says that you can work out a deal with the utility that the utility can tell your inverter to operate at a different power factor, which simply means the current source measures when the peak voltage occurs and shifts the peak current to either leading or lagging, and normally it's going to be leading because you're trying to correct for lagging power factor out there on the utility world. And so that's why they can do it. So let's see what else we have. Oh, and how's the heat energy replaced in this volume? Well, infiltration, I guess. It all depends what the volume opens to. If it's if I were to do it in my unit here, we've got about 1,800 square feet and 8-foot ceiling, so we're looking at 16,000 cubic feet of space that my water heater will essentially be in, and a water heating heat pump, which I intend to get as my next water heater. Uh, so what it's going to do is going to enhance, and in Florida, of course, we do so much air conditioning and so little heating, and almost no heating in the last year or two. Maybe the last 10 years, I can't remember turning on any heat. But so therefore, it's an enhancement to the air conditioning, and it reduces your air conditioning costs as well. And the heat is replaced generally through infiltration, but not necessarily infiltration. There's also other ways that heat gets into a space, whether it's through the attic, whether it's through the walls, whether it's through the windows. So you just need to give some thought to that, though. It's true that you can't just do it without thinking about the consequences. Otherwise, you might get somebody pretty upset about cooling off their space in the wintertime when they would really like to be heating it instead. So it works against you in the winter, but it works for you in the summer. And so therefore they're great for Florida and not maybe quite as great in New York or Minnesota. Let's see, normal water heater take about 8 solar panels, so the average family with the heat pump water heater, 2 solar. Yeah, I agree. I just did that calculation. On the other hand, you don't want to put solar panels just to heat your water if they're making electricity. You want to feed your main distribution panel so that when you're not heating water with that electricity, it's there, your solar is still making the electricity. You want it to go elsewhere as well. But yeah, that sounds about right. Looking out, you can convert BTUs. A typical solar water heater be 30 for 4 people, 80-gallon tank, 37,000 BTUs per day. Do your conversion, BTUs per watt, and so forth. Yeah, there's some really neat math you can do, and yeah. So that's what I'm saying, Greg. In the Northeast, it may not be quite as attractive to have this in your conditioned space, but it's probably still okay to have it out in the garage. And then you might even encourage a little infiltration so it doesn't make it too much colder there. But if you're heating your garage, it's going to oppose it. And yes, you need to look at heating degree days. And it's not as efficient installation in the Northeast as it is in Florida. And the other thing about Florida is if you're trying to heat water, the coefficient of performance increases the hotter the ambient air because there's more heat in it to be absorbed. So let's see, what else have we got here? We covered all these. If you would, though, folks, please type in on the Q&A, because here I have to read through the whole thing to see what's there, whereas on Q&A I get to X them out after I've answered them. And let's see. And I don't necessarily have all the answers. You probably noticed that. I do have a few, and I've been in this for a while. All right, I think we got all the chats now. I'm going to close out the chat, but I'm going to encourage you to use the Q&As now so that we can, and there are a couple there. Let's go to them. Converting wind energy to electric, is there a negative impact on wind patterns? Well, sure. I mean, obviously, if you've got a wind pattern that you like, and if you put a windmill in front of it, if you're taking energy out of the wind, you're going to slow down the wind a little bit. And I am not a wind expert, but I know that it is very interesting deciding where to locate the wind machines, especially if wind comes from different directions, because then they have to be rotating and you need certain spacing to make sure that the wind to one of them doesn't interfere with the wind to another one of them. I do have a friend who designs these things. He works out of Costa Rica because they're almost 100% renewables in Costa Rica, and a lot of that is wind. They're wind, hydro, and solar. Let's see, how do I get 3.5 kilowatt hours of heating with only 1 kilowatt hour of electricity? That's the coefficient of performance. What you get, yeah, okay, but your thermodynamics class tells you got to consider all possible sources, okay? I wondered about this as well, but what's happening, Mark, is if you look at a refrigeration cycle, you've got electrical input, and what you're doing, let's consider a split system in a house, okay? And if we have a split air conditioning system in a house, you're basically putting electricity into a compressor, and that's compressing a gas to become a liquid, and in the process it gives off heat, which is then vented to the outside, and then it's recirculated again to the inside where it goes through an expansion valve where it evaporates, and when the liquid evaporates, especially a refrigerant, it takes in heat from the surroundings, which basically then cools the indoor air. And then it's recirculated back through the system, compressed again, the heat's removed, and back, and that cycle continues. Well, with the water heating heat pump, what you're taking, and it's this whole discussion about it getting colder outside the pump, that's because not only are you using the electricity to heat the water, but you're using the ambient air to heat the water, which you're using by means of this refrigeration cycle, where you get high SEERs for or if we just use coefficient of performance, the coefficient of performance says you get 4 units of heat out per 1 unit of heat in by means of electricity, and the other 3 units come from the ambient, and it's the compressor and all these valves and all these cooling coils and heating coils and stuff that make that possible. And that's basically how your refrigerator works as well. Let's see, negative impact when I answered it, maybe not a good enough answer, but it's the best I can do. 3.5 kilowatt hours, 1 kilowatt electricity. Okay, and yeah, it almost looked like a violation of the second law of thermodynamics, but no, it's not, because you're using water, an additional energy source, which is the air surrounding the heater, which is you're taking energy out of it. Air conditioning wouldn't work either unless this were possible. Water heater, 8 solar panels. Okay, we did that one. And okay. All right, so now, okay, and when Mark said thanks, so I can answer that, say you're welcome, and that one's gone. Okay. Fine, and I appreciate all the questions, by the way. That's what this is supposed to be. This is supposed to be an interactive session. Let's see if my phone will tell me the time now. Come on. My display on my phone has changed. I must have pressed something at some point and screwed that up. All right, time, look at my other clock. We're okay. All right, let's move on to some more stuff here. Some of the trade-offs are, for example, and there's a question, we'll pick up on that in just a second. If you can put more efficient appliances in, then you can use a smaller solar array. So you have to evaluate the cost of putting in a more efficient appliance versus the savings of using a smaller photovoltaic array. And that's what makes engineering interesting. I mean, otherwise it can be pretty boring just using a bunch of tables and stuff. 3,413 BTUs per kilowatt hour, da-da-da-da. So yeah, here. This is the fun part here, folks, is looking at the trade-offs and try to optimize. Now, one thing that's going to make this less fun is there are a bunch of artificial intelligence programs now that are about to hit the market. Some are already there, I think. College of Architecture at Florida Atlantic University, where I used to work, they are doing AI, and it focuses on making buildings most efficient in the most cost-effective way. So pretty soon there's going to be a computer program that will do this for you. And maybe it's there now. I'm not sure. I don't do total design, so I haven't watched the market closely enough. In any case, you just compare the costs, and you either put in more PV or less PV or more efficiency or whatever. And it's not just efficiency, because, you know, if you got a 200-watt TV screen, and if you run it for 8 hours a day, that's a lot different than running it for 2 hours a day. So use is also an important factor that is, basically involves wild guesses. Because unless you're doing it for yourself, when you know your habits, you have to guess at what the client's habits might be. We're going to show orientation things for photovoltaics just to get an idea. Because if you can't install a photovoltaic array facing south, maybe you can do it west anyway and still have it cost effective. And if you're considering a building load, electric vehicles are going to be important. We're going to look at that in a minute. Looking at Albany, because I'm guessing quite a few of the folks on this webinar are in the Northeast. The best orientation of a photovoltaic array is a 30-degree tilt facing directly south if it's not a tracking array. And you just don't put tracking arrays on the roof of a residence. They're mostly reserved for ground mounts. So 100%, this is not 100 of anything other than percent. So your optimal orientation is 30 degrees facing south. If you face it south at a tilt of 45 degrees, you only lose 1%. All right. If you lay it flat, you lose 13%. If you have it vertical, you lose 33%. All right. So somewhere between 30 and 45 degrees looks pretty good. 60 degrees, you lose 7%. Okay. But what if you face it west with a tilt of 25 degrees? You lose 17%. Well, okay, so that's your kilowatt hours are going to probably cost 17% more now. Instead of 6 cents. But you know, that only raises it 7 or 8 cents, and in the Northeast you're paying 17 or 18 cents a kilowatt hour, so it still makes it a worthwhile investment to face it west. Okay, and if you can face it west at a 10 degrees tilt, then you only lose 14%. So this just gives an example, and you can calculate. This is all comes off the National Renewable Energy Lab's system advisory model site. So you just put your orientation and your location in, and it cranks out exactly how many annual kilowatt hours you're going to get, and it does it on a monthly basis. So if you want to design for more generation in a certain month, you can take that into account as well. So this is a great program for, and there are other, this is free, but there are commercially available programs as well that cost more money because they have more weather data and more bells and whistles. Let's see, another Q&A up here. Let's look at it. Oh, it's 11:29. Okay. Thank you. Okay, so just the thought here that west and east are not out of the question. They just end up costing ever so slightly more to make the electricity because you don't make quite as much, or you need to install more to make the same amount. So let's take a look at the bottom line. Here are 6 United States cities. Excuse me. And what we're looking at is the additional mortgage cost in order to build a zero energy building. Okay. So if in Atlanta, we want a zero energy building rather than one that just meets the minimum energy code, this same building, and I don't know the exact same size, but these are relative numbers, they're scalable. We're talking about initial investment of $19,548. That's obviously a computer program. I'd be perfectly happy to say an extra $20,000. But in any case, it's going to save $152 a month on the energy bill, and the mortgage cost is going to be $100 more. So here's a $52 every month. You got $52 extra in your pocket that is tax-free, because this is savings that's not coming out of a savings bank. It's just money you did not pay on your electric bill. Baltimore, you got $167 versus $81. So even more savings if you go zero energy in Baltimore. New York, I'm guessing more of you are from New York than from San Francisco. Look at your savings, $99 to $189. $90 of extra money in your pocket for an extra $19,000 investment, just about the same as Atlanta, to go zero energy. So, why not? Optimize your choices, go zero energy, save the planet, and save an extra $200 a month for lunch, or 189, whatever. So this is impressive. When I saw this, I almost jumped out of my chair that folks had gone through and done a very comprehensive analysis here. So retrofits, yeah, there's that too. Lots of existing buildings. Most can be greener. So again, this is stuff you can read when you order the slides, but a lot of things to do. And there's computer programs out there. So you don't have to guess at these things. You put in some numbers, you know how big the space is going to be, how high the ceiling is going to be, how many windows there are and stuff. So you plug in these components and then press the button and see what it does for you. Because they analyze the envelope, equipment, and they do cost effectiveness analysis. One is the Building Energy Optimization Program from National Renewable Energy Labs. And if you Google that, they'll probably let you use it for a month for free. Florida Solar Energy Center has been working on these buildings for a long time. They got two versions of Energy Gauge, residential version and tall buildings version. And they'll let you download that per month to practice and see if you like it. And there are more and more coming out all the time. And like I mentioned there, I don't even have the names of any of the programs that use artificial intelligence, but interesting. And of course, SAM is a free download as well. Let's see what we got here in the Q&A. Looks like payback was 20 to 30 years on initial investment, correct? You're talking about, yeah, I guess so. But we're talking about a mortgage here. And what we're saying is that, and if they used a life cycle costing analysis that included maintenance, so what we're talking about is maybe it's a 30-year payback, and maybe you can take that money and put it somewhere else and make more money on it. That's always true. On the other hand, your actual operating cost of that building is less if you spend the extra money up front and include it as part of the mortgage. So yeah, and that's why payback bothers me, because this is where the government needs to step in. We're going to talk about government in a minute. If people are going to insist on a 2-year payback, then these things don't work. And this happens in business. People want a 2-year payback. For me, I'm perfectly happy to have my electric bill less than my mortgage payment, because that means every single month for the next 20 or 30 years, I'm going to have extra money in my pocket, which if I want, I can invest it. And I can put it in the bank, and I'm going to make more money because it's going to presumably earn interest. So you got to take that into account as well in terms of 20 or 30 years payback. But I'm glad you noticed that, because these are things that people are going to talk about, and you need to have an answer. All right, let's see. Where are we now? Ready for the next slide. Vehicles, okay? Numbers again. I know y'all want these numbers. So, gallon of gas, every time you burn a gallon of gas, you're dumping 19.6 pounds of carbon dioxide into the atmosphere. Coal-generated electricity, 2.2 pounds of carbon dioxide per kilowatt hour. Natural gas, 0.9 of a pound per kilowatt hour. Renewable generated electricity, no carbon dioxide per kilowatt hour. So let's look at an average car. 25 miles per gallon means 80 pounds of carbon dioxide per 100 miles driven. Okay, for a gasoline car, if it's at 25 miles per gallon. An electric car gets 3 to 4 miles per kilowatt hour. We happen to have a plug-in hybrid, and since the pandemic started, actually we have not added gas to that car since last December, almost a year ago now. So we're basically running on electric, and we get 4 miles per kilowatt hour with ours, okay? So this is a very realistic number. So if you get 4 miles per kilowatt hour, that means, and you're using natural gas generated electricity, it means in 100 miles you're releasing 25 pounds of CO2 rather than 80 pounds. And that 25 pounds is being released by the utility, but if it's renewable electricity, then there's no additional carbon dioxide released by this renewable car, or this car with renewable electricity. So if you're designing a building, why not design it for an electric, include some solar for the electric car charging as well? And we're going to look at how much that takes in a minute. Here's a little comparison. Here's your electric vehicle, 10,000 miles on renewables, no carbon dioxide. Maybe your electricity is costing 15 cents a kilowatt hour. I'm using 8 cents kilowatt hour electricity here because we're on the general service demand rate, and we charge at night, so we don't contribute to the demand. 3,000 kilowatt hours a year for 10,000 miles with typical miles per kilowatt hour. So you're talking $450 for your fuel for that year, no emissions of carbon dioxide, and your batteries are available for utility storage when you're charging the vehicle at a charging station. And that's an interesting situation right there as well, because once bidirectional charging is universal, your car, when you plug it in, it'll start talking to the utility, and the utility will ask you if it wants electricity, or it'll ask it if it wants to sell some. And they will negotiate between your car and utility, based on information you give your car, how much your car is willing to buy electricity from on off-peak, or how much is willing to sell it for when the utility needs it. Very interesting stuff. Here's a gasoline vehicle, comparable thing, 25 miles per gallon, 10,000 miles. That's 400 gallons of gasoline. So that's going to cost you around $1,200, give or take. 7,840 pounds of CO2 released, which is 3.56 metric tons. And if you've got 275 million of these on the road, which we have here in the United States right now, we're looking at 2.16 trillion pounds of CO2 released. And you'll note that that's pretty consistent with the picture we had earlier on. What about other stuff? Electric school buses. Florida's going to buy a bunch of these because we got some money out of a lawsuit against a settlement with Volkswagen on those diesel vehicles that they said were cleaner than they really were. Delivery trucks, electric, all electric. There's that fancy Tesla pickup truck. And electric trains. So these are out there, and they're already there. You can buy them, put them into use. There's other stuff too. These cute little things. These things. I don't even know what some of them are called. That's a hot motorcycle, though, believe me. That thing is probably going to beat any Harley on the market. Maybe it is a Harley. And a little cute little electric van. So these things are here. You buy them now if you want to. Maybe somewhere in India and other countries. Zhengzheng, I think it's a city in China that's going all electric. The Norwegians are going all electric by 2005. So clearly electric is what we're looking for. So how much additional renewables do we need for 275 million EVs? Well, again, you do the math. That's what we do. We're engineers. In other words, if we replace this with petroleum with electricity, well, again, if we do 10,000 miles a year, 4 miles a kilowatt hour, it tells us that we're going to need 688 billion kilowatt hours a year for the fleet, or 2,500 kilowatt hours a year per vehicle. Now, this puts it on kind of a personal level, doesn't it? Because we were just talking about a kilowatt of PV will generate about 1,500 kilowatt hours. So this means we're looking at somewhere between, in the neighborhood of of 1,500 watts of photovoltaics per vehicle to generate the electricity it needs. So you add an extra 1,500 watts to your PV system, or 2 kW if you're going to drive a little more, and or if you have 2 cars, then add a little more, and off you go on carbon-free electricity. So if we're going to do this, it means $688 billion or kilowatt hours per year and $1.3 trillion over. But this is money invested by the consumer in order to save money on operating costs for this beautiful little electrical vehicle, which the car dealers are having all kinds of mixed feelings about because they're losing money on repairs. I mean, that electric motor lasts for a long time. The batteries last a long time. We take ours in and get it washed and cleaned once a year, and they put a little bit of anticoagulant stuff in the gasoline because otherwise it would turn into gelatin. But otherwise, and of course the tires wear out. But anyway, 130 million a year over 10 years. Add that to what we mentioned earlier on the cost to replace all the fossil fuel, or at least the methane and the or natural gas and the coal, and now we add petroleum to that, and it adds another 130 million a year. But probably not a government investment. This is going to be invested by people who are trying to make money on their investment. All right. Now, the other thing is energy efficiency. If we build all that solar and at the same time clean up the energy efficiency and have more efficient buildings, then we're not going to need as much solar as we originally imagined. So we're going to have some leftovers for vehicles, and maybe this $130 million is more than we're really going to need. All right, here's so what's going to happen to the grid? Well, there are things that we've had pumped hydro around for a long time for storage because they use that for a nuclear base load, and battery storage is going up fast. Let's see what we got for time here. It's about 10 to 12, it looks like. So I'm going to hold on, if you don't mind. We're close, and I'm going to answer all the questions that are remaining at the end. So here's some storage options for the storage for all the solar and stuff. And pumped hydro, battery storage, flywheel, supercapacitors, weightlifting. We talked about all these things. But now we add the extra 100 million electric vehicles. And that means we'll probably have somewhere close to 600 million kilowatts and 1 billion kilowatt hours of power and energy available just from the vehicles out there that are parked while we're at work or in the grocery store, wherever, parked into a vehicle charger. So what is the message here? It says that we're going to be designing a whole lot more vehicle charging stations into the structures in the whatever we've got starting to put in parking lots now. They're starting to put in vehicle charging out at the university here locally. They have some EV charging stations. Libraries have some. Cell phone parking lots have some at airports, and there will presumably be a whole lot more because it's going to be seen that this is a great investment. Now, of course, we got some interesting grid protection issues here in terms of reverse power flows. We can't have so much renewable electricity out there that it's going to try to run our generators backwards. We're going to have to either cut back on the renewable generation, or alternatively just save it. And the storage option is clearly going to be the one that becomes most attractive. Another thing is stabilization of voltage amplitudes at substation levels, because if we have clouds going over and then all of a sudden we need more electricity from the grid, then the taps on the transformers at the substations have to change, and if they're mechanical taps, they are going to have to be replaced more often. So, but that can be fixed. These can be made electronic switches rather than mechanical switches. So yeah, there are some issues with utilities, but they are all solvable, and they all involves some work for engineers and architects. So what about the grid? Here's what we have now, and here's what we'll have in the future, more than likely. Okay, simply a whole lot more renewables, a whole lot more storage out there at a number of different levels. Need to talk a little bit about the government, okay? And the government is presumably of the people, by the people, and for the people. There's some of the people, okay? We can green the buildings. I'm just going to flick through this here so we can make sure we have time for questions. You can read this. But this is what the government can do, and this is what our friend Greta has been asking for. And these are things they can do whether or not we do what we need to do. These can help us to do some of the things that we want to do, okay? But a lot of those things we want to do are already economically attractive and they don't need the government's help. So we need to keep that in mind, and that's going to be a driving force. We may get more help from the government now, we'll see. But we can still keep going because it is still more economical to make the choices we've just been talking about. One of the things is this payback thing, and we need to have some kind of a deal with industry where they can collect their payback up front or something like that. I'm not exactly sure how that should work, but I would suggest maybe we need a committee to think about that. People who are a lot more astute at money and making industry happy. Where our money goes can make a difference. Folks are trying to get these people to stop lending money to fossil fuels and put it into renewables instead. There's some out there. Here's the bottom line. You need to see that. Because if we meet the Paris Agreement, and this is a bunch of economists got together and drew this picture, and we can't do the whole picture and still have time, but you can look at this when you order the slides, and you'll see that the red line is what happens to the economy if we don't go the green route. And the green line is where we go with the green route. And if you just do some numbers here, between now and 2100, the difference is roughly $68 trillion, okay, cumulatively, that we lose in GDP by not going green. I mean, that should be a pretty good argument. Different sectors are affected more than others. A little picture here of the Iowa flooding and Nebraska flooding last year. Cost an awful lot of money. It'd be nice if we didn't have to spend that every year. Need some greener ethics, maybe. And it's interesting because it's the ASCE, and I think most other now professional organizations have included sustainability as an important part of their code of ethics. So it's out there, it's happening. And we need to do it now. And I hate to sound like Greta, but in a way I'm happy to sound like Greta because I just happen to believe that she's a pretty bright young lady and we need to listen and we need to act because we're going to be doing it for her and for our children and grandchildren. So when all is said and done, let's have a lot more done than said, all right? So that's it. Now, what I want to do is take a look at it, at Q&A here. Okay, and it also takes another 4 pounds of CO2 to refine a gallon of gas. Thank you, David. So we're talking about not just the 19.2, but then I suppose we talk about the CO2 it takes to build various infrastructure too. We're talking using, we could argue there's some CO2 does go into solar because we have to drive vehicles and we have to manufacture the cells and stuff, although this is an interesting observation because a photovoltaic cell will generate roughly 20 to 40 times more electricity over its lifetime than was used in making it. So when you start installing and so forth, it's still a positive return on investment of about 10 to 1. So So yeah, if we're going to count everything, we need to talk about the cost of creating it, and that's refining it. And then you also have to drill for it and do the fracking, and what's the cost there, and is there an environmental cost? And we can make this as complicated as we like, you know. 130 billion per year. What did I have? I don't remember, and I don't think we have time to get back. It's 1156. I don't know if we'll go back for that. 130 billion per year. What did I say? It was 1.3 trillion over a 10-year period, wasn't it? Something like that. Russ, if you wrote that down, that would help me save me that. Oh, wait, no, I can maybe, I'm still screen sharing, so you can see my entire screen now. Or maybe you can't. Maybe you can only see. Let me see if I can find that. Fleet replacement. Come on, electric cars, where are you? What's that? No, not that one. This one? Oh. Yep. Okay. Thank you for. I've got 130 million. It's 130 billion. You're absolutely right. I will make that correction. Thank you very much. 130 billion a year for fleet replacement. That's only off by a factor of 1,000. Isn't that getting a little picky? All right, Russ. Thank you. I appreciate that. I am glad I found that. That was one of those careless mistakes. That's why we have other people review our work, because once in a while we do mess up. Thank you. I hope that's the only one, though. This slide is here because somebody said, "Hey, you didn't tell us what it would cost," and I made this slide. 4 pounds to refine a gallon of gas. I need to know that. Okay, let's see. Any other questions or anyone else? Any other comments anybody wants? I'm not going to. I don't see any more. Here's something over here in chat. Let's see what we got for chat. Okay, here's about the quiz and the slides and stuff like that. Okay, and so be sure to check the chat box. And okay, the people asking what slide was, and we're talking about slide 43, which I just found. I had million instead of billion. My apologies for that, and my thanks to you for fixing it. And I've got 11:59. I don't think here's another Q&A here. Let's see. Okay. Thank you, Mark. You're more than welcome. My pleasure. I hope everybody found this was worth watching, worth listening to. Hope you got something from it, and I hope you can put it to use, because I think it can probably help your bank account and help the planet. And what could be a better combination than helping your bank account and the planet at the same time? Okay. You will have a chance to evaluate it. We welcome comments. They'll be offline. They'll go on the website where the course shows. And don't forget to take the test if you need to. And if you need more online live credit, let the host know what you might like to hear about. Maybe you want to learn how to design battery backup photovoltaic systems or something like that. We can do that. We got one of those. So meanwhile, I hope you all enjoy the rest of your day and the rest of the week. I hope you stay healthy. And may next year and the years to come be better than what we have right now. Okay, what I'm going to do, I'm not going to sign out until